In this video, we solve problem 11.5.054 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the equation, or an equation, it should say, of a plane with the given characteristics. We're told that the plane passes through these 2 points and is perpendicular to another plane with a given equation. So let me change this. I want to find an equation for the plane, because remember, we have infinitely many equations of the plane. Like I could take this equation of a plane and I could multiply it by any constant I want except for 0, and I'll still have an equation of that plane. All we will have done is make all of the integer coefficients and the number on the right-hand side a little larger. So there are infinitely many equations of any plane, and we just want one of them. Okay, so we want a plane that has these characteristics. It passes through these 2 points. Now, it's hard to draw a plane in 3-dimensional space, so I'm going to draw a little cartoon of a plane. And of course, we're imagining that this goes off in all of the directions. It extends, but I'm just drawing part of it here. And we'll say that this point is the point P. That's how I'll choose to label it, with coordinates 3, 2, and 1. And this is the point Q, also in the plane. And that has coordinates 3, 1, and -7. Now I'm told that my plane, the plane that I've drawn here, is perpendicular to another plane. So I guess we have to imagine a second plane that meets it at a right angle. So I'll try to draw a plane at a right angle to this one. We just do the best we can. So let's say that's where that second plane meets our first plane. And the equation of this second plane, I'll just shade it in. Plane number 2, not our plane, but the other plane, is 6x plus 7y plus 3z equals 17. And this is a right angle, and this is a right angle, and that's a right angle, and that's a right angle. Question becomes, okay, well, how do I find the equation of this plane? Well, remember what we know about planes. First of all, the equation of a plane passing through a point x naught, y naught, z naught with normal vector with components a, b, and c. So a times I hat plus b times j hat plus c times k hat a plane with those characteristics has the following equation. So we've got a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So that's what we need. We need both a point in the plane and a normal vector to the plane. Now I've got points in my plane. I know that P is in my plane and Q is in my plane. So the x naught, y naught, z naught is covered. I could use this as my x naught, y naught, z naught, or I could use that as my x naught, y naught, z naught. The question is, how do I find the normal vector? How can I find a vector that is guaranteed to be perpendicular to the plane containing these 2 points? Well, one thing I know for sure is that this normal vector has to be perpendicular to every single vector in my plane. So if Q is in the plane and P is in the plane, one thing that I know for sure is that my normal vector is perpendicular to the vector PQ, or we tend to say orthogonal. So let's write this down. Now, we may not use all of these facts that we collect about our plane, but this is the information that we have. We know that the normal vector, which we need in order to find this equation of the plane, must be perpendicular to PQ or orthogonal to PQ. Oops, let's write it that way. And that means that the dot product of PQ and N must be 0, because we know that any two vectors that are orthogonal to each other must have a 0 dot product. So I don't know what N is. Let's just say that N will have components A, B, and C. So given that, I know that this vector with components A, B, and C has to be perpendicular to the vector from P to Q. To find that vector, I will list the coordinates of Q, which are 3, 1, and -7. So that's my terminal point, and then I will subtract the coordinates of my initial point. So subtract 3 and 2 and 1. And that dot product is 0. So let me simplify the components of my vector PQ. And we keep going. If I want to take the dot product of these two vectors, it's actually very simple. We just multiply and add. Multiply component by component and add. So we have A times 0 plus B times -1 plus C times -8. And that result is our dot product. And that has to be equal to 0. So I've got -B minus 8C equals 0. And that's nice. I don't know what A is, but I know that B and C, those are the F or the Y and Z components of my normal vector, have to satisfy this relationship. So I think I will take this and I will solve for B. If I add B to both sides and then sort of switch sides, I have B equals 8 or -8 times C. So if C happened to be 1, B would be -8. So that's nice. That's an important fact that we may need. But I still need to be able to find this component A. I need to be able to find the X component of my normal vector so that I can do this. Let's think about other facts that we know. Well, we also know that this second plane is perpendicular to our plane. And if this plane is perpendicular to our plane, that means that the normal vector for this plane, which I could draw down here, well, you could draw it anywhere, but it's a little bit difficult. The normal vector to this plane and the normal vector to my plane have to be at a 90-degree angle to each other as well. My picture is pretty bad, I'm sorry. But yeah, the only way that this vector or this plane is perpendicular to this plane is if this vector and this vector are orthogonal to each other. And I can just look at the equation of the plane and infer one of the normal vectors to that plane. Remember from our study of planes that if you just look at the coefficients of x, y, and z of this equation of the plane in general form, you'll find the components of your normal vector. So our normal vector has components 6, 7, and 3, or the second plane has that normal vector. And we're trying to find our first normal vector. Since we know the planes are perpendicular to each other, that means the normal vectors are orthogonal to each other. So I can write that down. Our normal vector is orthogonal to the normal vector of the second plane. And that means that those two must have a dot product of 0 as well. So we don't know what A, B, and C are, but we know that the second normal vector or a normal vector of that second plane can be written this way. It has components 6, 7, and 3, and we know the dot product has to be 0. So if we compute this dot product, we have 6 times A plus 7 times B plus 3 times C equals 0. And remember, again, we're trying to solve for A, B, and C. so that we can find the components of that normal vector. And once we have the components of the normal vector, we can use that and one of these points as our x naught, y naught, z naught, and just substitute in and simplify to find the equation of our plane. And I think we're on our way. So this is pretty cool. I've got one equation relating B to C, and I've got another equation relating A, B, and C. Putting those two together, I've got two equations with three unknowns. I can bring that down to one equation with two unknowns by making a substitution. So since I know both of these are true, I know I can replace B in this equation with negative 8C. Just substituting, no big deal. And so we get this. And so from this equation, I can find out how A must relate to C. I have 6A equals 53C. And if I divide both sides by 6, I find that A would be 53 over C times 6. So this is nice. You may initially be thinking that, okay, don't I need three equations with three unknowns in order to find A, B, and C? Actually, we only need two equations with three unknowns, and I'll tell you why. What we've just found is that for our normal vector with components A, B, and C, is as long as A is 53 over 6 times C, and B is negative 8C, and C is just any old number, except for 0, of course, this vector will be perpendicular to our plane. Now, if you're saying to yourself, I don't really like having that extra C, remember what that extra C would do. That's just changing the length of the vector. So if I choose C equals 6 to get rid of that 6, that'll get rid of my fractions, and that'll be really nice, and I'll have a vector that is a certain length. But if I wanted to, I could choose C equals 1. I'd have 53 over 6 here, and negative 8 is my y component, and 1 is my z component. Or I could make C equal 100. Typically, we want the components of our normal vector to be small integers. Now we can't make them that small because we've got this 53. But in order to get rid of this fraction, I can let C equal 6 or choose C to be equal to 6. And that will give me a normal vector to the plane. And remember, we only need one normal vector, but there are infinitely many normal vectors. I could have this one, or I could have the one that's 6 times as long. I could multiply it by -1 and have the normal vector that's pointing in the opposite direction. Any one of those normal vectors will do. And we just tend to choose the one that has components that are small positive integers. So that's the plan. So let's let C equal 6. Then our normal vector is 53 over 6 times 6 by design. It's going to be 53 for our x component, negative 8 times 6 for our y component, and 6 for our z component. So my A, B, and C are 53, negative 48, and 6. Okay, so now we can just go to our equation of a plane. And we can use any point in the plane as our P, our x naught, y naught, z naught. We had P over here equals 3, 2, 1. I will choose for that to be my x naught, y naught, z naught. So when x is 3, y is 2, z equals 1, and z equals 1. And now we'll just substitute. I've got A times x minus x naught plus B times y minus y naught plus C times z minus z naught. Initially, I'm just going to leave spaces for all of those numbers, and then I'll substitute them in. X naught, Y naught, Z naught is 3, 2, 1. So we have a 3 here, a 2 here, and a 1 here. And then my coefficients, A, B, and C, are 53, negative 48, and 6. And that is the equation of the plane. We just have to simplify it, and then we'll be done. 53x minus 159. Negative 48 times y is negative 48y. And then we'll have negative 48 times 2. What's that, 96? Oops, I forgot my y for a second there. Distribute the 6. We get that. And then we would combine everything, combine those constants and move them to the other side. So we'll have 53x here, and a minus 48y, and a plus 6z equals, and I'll move that 159 to the other side by adding it to both sides. And this 96 minus 6 is 90. I have a positive 90. I'll subtract that from both sides, and I get 53x minus 48y plus 6z happens to be 69. And that is our equation of the plane. And remember what we said earlier. Oops, these are notes from a different class. That plane should pass through the points 3, 2, 1 and 3, 1, negative 7, and it should be perpendicular to this plane. So if we want to, we could check our work by making sure that x, y, z equals 3, 2, 1 and x, y, z equals 3, 1, negative 7 satisfy that equation of the plane. And we can look at the normal vector of our plane and take its dot product with the normal vector of this plane, just to be sure that this normal vector and that normal vector are perpendicular to each other or orthogonal to each other, which is what happens when the planes are perpendicular to each other. So let's check. We know that the point P equals 3, 2, 1 is on the plane. To be certain that 3, 2, 1 is on this plane, I will substitute x equals 3 and y equals 2 and z equals 1 into the equation of the plane. Put a 3 here and a 2 here and a 1 there. And then we get 159 minus 96 plus 6. So we get 159 minus 90, and there's 69. That's the right-hand side. So 3, 2, 1 satisfies the equation of the plane, which means that point really is on the plane. Let's check the other point. We were also told that Q, which has coordinates 3, 1, and negative 7, is on the plane. So let's check by substituting into the left-hand side. Replace x with 3, replace y with 1, and z with negative 7. So we've got that 159 again. We're subtracting 48. We're also subtracting 42. And negative 48 minus 42 is negative 90. And so we get 69 there, which is the right-hand side. So that point is on the plane. And the last thing we want to check is that the two planes are supposed to be perpendicular to each other. Plane number 1, that's our plane, is perpendicular to plane number 2. And we know that that's only true if the normal vector to our plane is orthogonal to the normal vector of the other plane. And we know that that's only true when the two vectors have a dot product of 0. So our plane has a normal vector with components 53, negative 48, and 6. So we're checking this again. We're just going to compute that dot product. I'm not saying that these are equivalent yet. So I want to show, or I know that all these statements are equivalent. I want to show that this dot product is actually a 0 in order to check this. So my normal vector is this. The normal vector of the given plane had components 6, 7, and 3. And so this is what we have. We've got 53 times 6 plus negative 48 times 7 plus 6 times 3. And I think I'll just use my calculator for the arithmetic this time. And I get 0, which is what we should get if the two vectors are orthogonal to each other, which means the planes are orthogonal to each other. Okay, so that's it. One more time through the process. How do you figure out this problem? Well, first of all, I would draw a picture. I would plot the 2 points that they gave me. I say that those 2 points are on my plane, and I'll draw that perpendicular plane. And then I think about what I need. If I'm trying to find the equation of the plane, I need a normal vector and a point in the plane. They gave me 2 points in the plane, so that's good. The only thing that's missing for me is this normal vector. And the question is, how can we find that normal vector with the information that we were given? And the way we found it was we created a vector from this point P in the plane to the point Q in the plane, and remembered that every vector in that plane has to be perpendicular to our normal vector. So even though I don't know what my normal vector is yet, I know that its dot product with PQ has to be 0. And that led us here to this equation that related B to C. And then we said, okay, what else do we know? Well, if these two planes are perpendicular to each other, then their normal vectors must be orthogonal to each other. So this must be true, which means the dot product must be 0, which gives us the second equation. And again, a lot of students might think, okay, I must need 3 equations and 3 unknowns because I'm looking for 3 unknowns over here, A, B, and C. But actually, one of those numbers can be anything we want. And the reason that one of those numbers can be anything we want is because we can always resize our vector by multiplying by a constant to make that normal vector longer or shorter, or to flip it so that's going in the opposite direction. There's a lot that we can do with that. So we don't need all 3 variables to be specified. We just need 2 of the variables specified in terms of the third. And we already had B in terms of C. When we had B in terms of C, we were able to find A in terms of C. And then once we had A in terms of C, we knew this would be our normal vector for any C. And then we just chose C to make all of these integers. So I chose C to be 6 to get rid of that 6 in the denominator. And then once we had our normal and a point, we just substituted into the equation of a plane and simplified. So that's how we handle that question. Please let me know if you have any questions. Happy to help.